dear ladies and gentlemen, I give you a very warm welcome to our seminar here in Tumlingen, the main station from where you send your warm greetings to our International Engineer and Designer Seminar. My name is Mark Wolfgang. I am civil engineer and worked since several years in the Fischer Academy, and will guide you today through the seminar and ask questions, because you have the possibility to ask questions. On your right panel on your screen is the chat function, so you can write questions in during the seminar, and we will try to answer your questions during the seminar, or if not possible, if it's too much, then we come to you after the seminar personally. I am not the only one who moderates the seminar here. We are two men, and I would like to introduce you Dr. Oliver Geibig, who is since some years by Fischer.
Hello, everybody. My name is Oliver. Also, warm welcome from my side. Yeah, we are happy today to provide you this online seminar on the topic of design of anchors. First time in lifetime of fastening technology, the design is implemented in a code, which is the EN 1992 Part 4, or shortly Eurocode 2, and with therefore there's a much more more mandatory aspect in designing anchors. And yeah, we will show you today how to design, what are differences between the former design method and also to the new method, which are the challenges, which are the benefits, and this we will show you in the next couple of minutes, so roughly 45 minutes. Yeah, thank you. Then I think we can start, and to really give you a very professional presentation, we asked our expert in the anchor business, who wrote his PhD in anchor design, and who is also in charge of technology transfer at Fischer in our headquarters here in Waldachtal in Germany. And yeah, warm welcome to our colleague and friend Thilo Pregartner.
Yeah, good morning, everybody. Good afternoon for those who are in a different time zone. Thank you for the introduction, Oliver. Thank you, Mark. As Mark already mentioned, you have the possibility to post some questions in the chat. Please do so, and I expect some really tough questions today, which I hopefully can answer then.
I would like to mention one more thing. We are asked again and again, if you missed something, can you see it again? There is the possibility to see it again. We will record this session and then put it on the web page, so there's possibility for you to see it again if you want. And now I wish you luck and you success and have fun. Thank you.
Thank you, Mark. Then we can start. So it's your turn, Thilo.
Perfect. Thank you, Oliver. My name is Thilo Pregartner. I'm obviously a German, but you may have noticed already by my accent. I'm a civil engineer, and I would like to talk today about design of fastenings in concrete, and about the new part of Eurocode 2, which is the part 4. So hopefully we tackle all technical problems. First of all, I would like to start with the short classification of the new part 4 of Eurocode 2 within the existing landscape of standards in civil engineering. So for design or for structural engineering, we have in Europe the Eurocode series, which contains the Eurocode 0 to Eurocode 9, with the two basis parts, Eurocode 0 and Eurocode 1 for actions on structures, and general the basics of structural design in civil engineering. Then we have the parts Eurocode 2 to Eurocode 9 for detailing and designing. We have one Eurocode for geotechnical design, and Eurocode 8 for seismic design. There are 3 Eurocodes in red boxes, which are the Eurocodes 2, 3, and 8. Why is that? It is because in general, if we talk about fastening technology in concrete, we try to connect steel structures with reinforced concrete structures. And according to the base material we are anchoring in, EC2 Part 4 was published as a additional part of Eurocode 2, and it's called Design of Fastenings in Concrete. A quick overview of the status before Eurocode 2 Part 4 was published. On the left side, you see as an example or as examples 6 different papers or documents or guidelines which were used before Eurocode 2 Part 4 was published for design of anchors. So we had, for example, Technical Report 029 for design of bonded anchors. We had the famous Annex C, which was the first ETAC part and the first European paper about the design of anchors in concrete. We have something for fire, we have something for seismic design, anchor channels, we had the technical specifications. All that changed with the publication of Eurocode 2 Part 4, which superseded all prior existing design guidelines in the framework of European technical assessments or papers that were published by EOTA.
Yeah, I already have the first question. We had that when we were running this online seminar in Germany. There was the questions, is this Eurocode 2 Part 4 already introduced? So can we already calculate according to Eurocode 2 Part 4? And the question, the second question on that is it still allowed to use the old one when we see that probably we are a little bit better with the old one?
So in general, Eurocode 2 Part 4 was published in all European member states, including the national annexes, which is, let's say, the first step for introducing it. And then finally, as an engineer, you always have to consider the actual state of the art. And with the publishing EC2 Part 4, more or less the state of the art in terms of design of fastenings in concrete change. So there are some changes which changed, let's say, utilization degrees and the performance of the anchors pretty rough. And in terms of that, the state of the art changed. Eurocode 2 Part 4, independent of legal specialities in the different member states and in the different countries, because in some countries it needs an additional step to make it legal binding also. Besides that, the state of the art changed, and it should be, at least in special cases where it has an influence on safety, it should be definitely considered.
Yeah, very good. So,
perfect, let's go ahead. Part 4 offers a lot of advantages, where some of them I try to summarize on this slide, which means with publishing it, the most recent state of the art in terms of anchor design in concrete was published. It is now a standard instead of a guideline, which changes the legal visibility of design of anchors in concrete. Besides that, the nomenclature and the safety concept of anchor design was adapted to the Eurocode 2 and in general to the Eurocode system. Besides that, you have a variety of different anchor systems that you can design with only one document, with, for example, metal anchors, adhesive anchors, but also cast-in-place solutions like headed studs or anchor channels. Pretty much the same is valid also for different loading types. So static and quasi-static loads are covered, of course, in EC 2-4, but also seismic design for seismic loads, dynamic loads, and design for fire attack. In general, EC 2 Part 4 provides a lot more transparency of anchor design in concrete and gives you in one document everything you need as an engineer outside. Perfect. One of the most important requirements that you have if you work with EN 1992-4 is the fact that in EN 1992-4 you can design only products that have a European technical product assessment. So EN 1992-4 was published in the framework of SEN, which is the European standardization body, and it provides general rules and equations for the design of anchors and fastenings in concrete. However, as input parameters for the design concept, you need details of the anchors. These details are called performance parameters, and performance parameters are published in European technical assessments, ETAs. Based on ETAs, you are also allowed as a manufacturer to affix a CE mark on your product, and you can get an ETA if for an ETA European assessment document exists. A European assessment document is also called EAD, and it provides the methods and criteria to derive the performance parameters which you need finally in EN 1992-4 to have a valid anchor design.
One question on that slide from my side. So you have the design method implemented in a code. Can you also imagine the performance parameters one day being integrated in a code, or do you don't see that for the midterm future?
We have already roughly 20 years of experience with qualifying anchors in the framework of EOTA. EOTA at the very beginning was an approval, not an approval body, but an organization for technical approvals. It changed in 2013 with the introduction of the construction products regulation to an assessment body. So we have quite some experience, and there are some details about anchor testing, which could be part of a standard for sure. However, currently the anchor manufacturers like the EOTA system very much because it's far more flexible and faster than the standardization work. So it is possible, but as anchor manufacturers, we don't like the SEN system that much because it's far too slow.
And probably too narrowed, so the topic of differentiation could be a bit more challenging for anchor suppliers.
Yeah. Okay, very good. So let's get to the center of the presentation today, which are more or less the fundamental changes which you face with the introduction of EC2 Part 4. And I tried to cluster them into 4 different topics, and then I filled them with detailed topics, which is then finally the list you see here. We have only 45 minutes. Of course, I could talk the whole day about this very interesting topic, but we don't want to bother you that much with it. So we focused on the 4 points which are highlighted currently in red, and I would like to go through it if there are no further questions currently. Okay, then let's get started with the general changes of EN 1992-4, and first of all, we'll talk about concrete strength classes. If you look at the old design guidelines like ETAC 001 Annex C, but also Technical Report 029, they covered a concrete strength class range between C20 and C50. If you look now into EN 1992-4, then you'll see that the range really got broader, and you can design now anchors in C12 to C90. However, we learned before that we are within a system, right? We have to consider that as a basis of a design, according to EN 1992-4, you need to have ETA assessed products. And there's currently still a gap, which means if you look at the corresponding EADs for metal anchors or for adhesive anchors, for example, then you see that in the EADs and also in the ETAs that were granted based on these EADs, the scope is still restricted to C20 to C50 as concrete strength class. So there is a possible amendment of the EAD in the future, and I have to say that we as a company already started working on that one in the EOTA working groups to get also in the near future ETAs that cover the whole compressive strength range which is offered.
Yeah. For you as an expert, the question, will it be more challenging to have the scope extended to the lower part, so C12, or to the C90? Which part is more challenging for us as an anchor supplier?
In terms of functionality of the products, the high strength part is more challenging, because you must make sure that, for example, friction-based systems are still working in the, let's say, relatively smooth and straight drill holes, which is the challenging part. In terms of design, it is restricted in any case until now, because the current equations for concrete-related failure modes are restricted to a maximum compressive strength of 60 megapascal. That even if the product is qualified in a C90, still the limit for the maximum concrete cone performance is limited by a concrete strength of 60 megapascal.
Okay.
Perfect. Then another topic which is pretty important and sometimes a bit strange if you look into the code in detail is that the reference of the compressive strength testing specimen changed. So in general, you have the possibility to measure concrete strength with 300 millimeter cylinders, as shown on the left, or 150 millimeter cubes. You see that already in the denomination of our concrete compressive strength classes. So we usually have two values that define a strength class. For example, C2025 means a cylinder strength of 20 megapascal and a cube strength of 25 megapascal. In these values, as they characterize the same and the identical concrete, you see already that there is a conversion factor in between, which has the value of 1.25 in low strength concrete and 1.2 in high strength concrete. Now, this difference in conversion between cylinder strength and cube strength, you have to consider in the CC method. The CC method has a lot of equations that contain dimensionful factors, which makes it sometimes a bit difficult, because you always have to use the same dimensions within the equation. So the first factor of it is not really clean of dimensions. Therefore, you have to consider this transfer to from cube strength to cylinder strength by additional factor. And if you insert the conversion factor of 1.2 under the square root, because the concrete compressive strength is usually considered under the square root in the equations, then you get an increasing factor of 9%. If you look now into the details, for example, into the characteristic resistance for a single anchor for concrete cone failure, then you see that between the old guidelines and the new EN 1992-4, the equation and the influencing parameters stayed the same. It changed the reference from cube strength to cylinder strength, and the factors, they also changed slightly, which means they got increased from 7.2 to 7.7 in cracked concrete and 10.1 to 11 in uncracked concrete. In general, you have to consider that even if you consider the cylinder strength already with the dimensional factor, still you have to insert the compressive strength under the square root, and that causes the fact that considering both the dimensional factor, which got increased, but also the compressive strength under the square root, the characteristics resistance decreased if you compare the values according to EN 1992-4 with the values of the old guidelines, which I tried to show here in this graph, where you see that a maximum decrease of this reference value of the characteristic resistance of 4.5% can be encountered. Besides, it depends on the concrete strength class, as the conversion factor changes, obviously, and they rounded it slightly different in uncracked and cracked concrete. So in general, if you compare really the results directly, you will find that the characteristic resistance, the baseline value, decreased. If you look now at different failure modes, I show on this slide concrete edge failure, which also contains a dimensionful factor, and compare the equations. Again, the cube strength changed to cylinder strength, The denomination of the first factor went from K1 to K9. However, the value stayed the same. So it is still 1.7 and 2.4 for cracked and uncracked concrete. Now, why is that? That is because during the development and the work on the new standard, EN 1992-4, they decided to reevaluate and reassess this complete failure mode. First of all, to make this conversion to the new compressive strength, but also to broaden the scope of the equation to larger embedment depth and in some parts also larger diameters. And with that, they still found that these two factors, 1.7 and 2.4, match the best the results of the tests and the finite element simulations that were basis of the scientific work for this equation.
Yeah, Thilo, I see that there are some questions, so we ask Mark to come and show and ask you the questions from the audience in order to do what we told our participants, that we will answer live also the questions. So
yeah,
go ahead.
Thank you
Mark.
very much. Thank you very much, ladies and gentlemen. I mentioned that you have the possibility to ask questions during the online seminar on your right panel with a chat function, and several of you did already. Thank you very much for those questions. One question was just in the beginning concerning seismic and also anchors with grout pads, let's say chemical systems. I think you mentioned already that there is the possibility it's included in the new Eurocode, but can you say maybe a comparison to USA, because there was the part USA, yes, they allowed, Eurocode not. We have it. Can you say a word in which kind is it inside? Because I think that question goes in that direction, that in earlier times in the ETAG was not included. If we speak from ETAs, for example, when we spoke about the assessments, seismic was not included. That means we had to look to the USA with the new ETAs assessment approval assessments. Now we have it. So that's new, and on top of it, the Eurocode came.
Yeah. Indeed, the US was, in terms of seismic design and especially seismic qualification of anchors, ahead of Europe. So they developed their qualification rules and testing rules up front of Europe. Finally, in Europe, it came slightly later, or slightly later, it came a few years later. But finally, it also got a bit differentiation between the systems. So in the US, they go back to 0.5 millimeter crack for seismic qualification, whereas in Europe we have two classes, which is seismic class or category C1, which is more or less comparable to the US category we have there, with a 0.5 millimeter crack. And then on top of it, in Europe, we have the 0.8 millimeter crack for category C2. And these two categories are distinguished in terms of design, depending on the ground acceleration and the importance class of your building. So there you more or less make the choice if you want to have, or if you need to design for category C2 and category C1. In the US, they catched up this topic with the C2 qualification also in the just recently, which means there was a new acceptance criteria by ICCS published recently, where the qualification according to the C2 category or similar to the C2 category is described. Which means the US is starting to adapt slowly also their system in terms of seismic design. In general, seismic design is completely included in Eurocode 2 Part 4, but also you need, of course, a product that is qualified for it.
Yeah, thank you very much. So another point for us Europeans, let's say that. Another question, I think that can be a short answer, ENSO. So if we look for the further part, I think that could be a short answer. What is ENSO and when is it needed? we say something about that?
Yeah, ENSO is a bit historical. So always additionally to the design guidelines, there was an additional design method published in the framework of FIB, which is a European but also a global concrete community. To make it short, not to explain too much about it, and there a advanced design method was published in the year 2011, which had some design regulations, recommendations, however you want to call it, which went beyond the content of the existing guidelines. So it was some kind of expert method, and the anchor manufacturer used this expert method in their design softwares to publish it as an additional expert design method. In Fischer it was called ENSO, but also other competitors use this method. With the publication of EC2 Part 4, now the state of the art changed, and a lot of regulations that were expert method in the FIB design guide got now more or less state of the art. So in general, this that if an additional design method going beyond EC2 Part 4 is necessary, that is currently questionable. But I hope that answers roughly.
Yeah, I think that is enough. So Enzo, who knows it from you, it's from the Further Times engineering solution, what was included in the Fischer software experience. We will have a look on it later. And one last question from a great man of the northern states is, you explained that there's the EAD, then the ETA gains, and those values are transferred in the equations of the Eurocode. What is when there is no EAD available?
Now that's the beauty of the IOTA system, and also the beauty of the construction product regulation as it exists today, is if you have a performance parameter or a application scope which is not covered either by a standard or by an existing EAD, you are allowed to apply for an ETA at a technical assessment body, and then the technical assessment body needs to work on it and create an EAD for you.
Yeah, okay. So far, I think now I'll let you continue.
Perfect.
And wish you success. You remember, you have the possibility to ask questions. Feel free. Thank you, Thilo.
Thank you.
Good, then while you focus on your presentation, I make sure that the technique is running here. Just give us a second.
Yeah, I would be lost without Oliver.
Yeah. Okay. So
perfect.
Now it should work again. Good.
Now let's have a look at one of the most important changes. If you look at EC2 Part 4 in total, compared with the guidelines before, and these concern verifications for tensile loads and especially adhesive anchors. The reason for this pretty big changes in terms of anchor design was an accident that happened in 2006 in the US in a road tunnel in Boston, where ceiling panels fell down on a driving car and a passenger got killed, where the root cause for this failure was the utilization of an epoxy resin which failed under permanent tensile loading. This accident caused a lot of additional research in the world of anchors. Adhesive anchors have one speciality. They have a special failure mode, which is called combined pull-out and concrete cone failure. Adhesive anchors have a variable embedment depth between 4 times diameter and 20 times diameter. You have a very flexible range of to choose your anchorage length, and coming with that, they also tend to change their failure mode, either with increasing embedment or with reducing bond strength. On the photo on the right, you see an adhesive anchor with a high bond strength and a low embedment, and you see a beautiful concrete cone failure and the anchor was able to activate the full concrete cone until the end of the anchor rod. Now, if you would install this anchor a bit deeper, or if you would reduce the bond strength due to temperature, for example, then you would get a failure mode which looks pretty much like that, where you get pull-out failure at the bottom of the anchor, and close to the surface is still a concrete cone failure. And this is covered in design by this combined pull-out and concrete cone failure mode. And there, the changes concerning this sustained loading behavior were introduced. And generally, you have two possibilities to test or to qualify an anchor for sustained loading, or to show that it's suited for sustained loading, which you have to do for any adhesive anchor which is qualified according to our EADs. One possibility is that you work with a relatively low sustained load, with a low creep load, and you measure the displacements of your anchor over time. Finally, you do an extrapolation of your displacement, and then you define a limit of maximum displacement, which you allow as safe. And you say, okay, if I stay below this limit, then my anchor is suitable for sustained loading. The other possibility is our so-called time to failure tests. In time to failure tests, you work with a relatively high constant creep loads on the system. They are roughly between 95% and 65% of the short-term reference value. And with doing that, you get relatively short failure times. Short means up to 6 months, a time frame that an anchor manufacturer is willing to wait for his ETA approval. And with doing so and putting these results of time to failure tests in a diagram, as it is shown here, you see on the y-axis the bond strength, and on the x-axis the time to failure in the logarithmic scale. Then you see that this transferable bond strength in time to failure tests, in creep tests, in tests with a constant tension load on the anchor, decreases relatively fast with increasing time to failure. These are the red triangles in my graph. These are the result of time to failure tests, where the blue diamonds are results of the short-term tests. Now, if you extrapolate these values of the time to failure test to the service life of 50 years, then you end up of roughly at a drop of the transferable bond strength at the end of the service life of your fastening of roughly 40% to a value of 0.6. And this value of 0.6 found then its way into the design equations for this combined pull-out failure mode. On the bottom, on the top left, you see the equations for the single anchor without edge influence and without spacing influence. Is calculated with a bond strength and a surface area, characteristic bond strength and a surface area. And then U in EN 1992-4 is this value psi sus. Psi sustained is a function of the value alpha sustained, where alpha sustained is the ratio between the creep-inducing permanent load and the value of the total load. So more or less, alpha sus shows you on how big the part is of a constant load, which is always on your system, compared to the sum of permanent load and variable load. If you draw now the equation of psi sus in a diagram, then you get this picture. Psi sus is on the y-axis, alpha sus is on the x-axis, and you see that psi sus stays 1.0 until the value alpha sus reaches psi null sustained. And then you start decreasing your characteristic resistance until the full reduction factor of 0.6, which is the red line here, once you reach 100% creep load compared to the sum of the meaning of the total loads. I'm sorry. Now, where do you get this factor of psi null sus from? The EN 1992-4 says, okay, you have to look into your European technical product specification. And if you don't find a value there, then please use the value 0.6. If you look now as an example at the ETA assessment of the FIS-SB super bond, then you find there already this reduction factor psi null sus inside, and it has values between 0.84 and 0.91. So in general, for you to remember, this factor psi sus can influence the design and the utilization degree of your applications very much. So it is the new state of the art, and based on that, you should give it a thought to consider it in the future if you have applications where you have a high percentage of creep-inducing load. Now we had enough reduction factor. Let's get to something a bit, let's say, which is also increasing our performance, and this factor is called CMN. It is a factor that you apply for the design for concrete cone failure in groups if you have bending and compression under your fixture. The factor is shown here in the equation for the characteristic group resistance. And the first example to show you what the factor is doing is an example with a relatively small bending moment compared to the tension load. So with the bending moment, you get a compression zone under your fixture, and the bending moment in combination with a tension load causes that the left anchor is pulled, and on the right side you have this compression zone. In this case, the ratio between tension load in the anchor and compression load in the compression zone is relatively small, and the inner lever arm, this value Z, is very big, and in that case you cannot apply any additional increasing factor. So CMN stays 1. This is also the case for applications close to edges. Now, if you have a big bending moment or a bigger bending moment compared to the tension load, you get this picture where you get a larger area which is compressed under the fixture, and this compression zone more or less influences the concrete cone of your pulled anchor, and like that you get an increase of the characteristic resistance. The equation for the factor of CMN is now shown on the slide. It is a function of the embedment depth and the inner lever arm. If you show it in a diagram, you get the picture on the left, which shows you CMN as a function of the ratio of the inner lever arm. At a theoretical value of the inner lever arm of 0, you get the maximum increasing factor of 2.0, and at an inner lever arm of 1.5, it reduces to a reduction factor. It is not a reduction factor, it reduces to the value of 1.0. On the right, you see the scientific background. I show it because it's always interesting to have some additional background with it, especially if you see that the first results go back to the year 93. So it took over 20 years that this very nice improving factor for special applications made its way into a design code. In general, it helps you for applications with large embedments, small spacing, or large bending moments. Good.
So we have some more questions. We should also have an eye on the time, and at the end we have also prepared some practical parts in our software so that this is getting also more tangible. Yeah.
Yes.
Mark.
Thank you, Thilo, for your presentation. Some more questions. I will ask you some of them. We will come to the others later after the seminar, but I think it is an important question. There was the question, could you please explain again why the Eurocode is mandatory? You did it already, but explain it again only.
For me, it is actually, it is the Eurocode series is in general a recommendation to introduce in the member states. So it is not mandatory for the member states. If it is mandatory in the member states, it depends very much on your legal requirements in terms of building law, which is pretty different. So I'm pretty firm in knowing that for Germany, and in Germany it is it goes via the MVVTB, which is a paper which is published by the German Building Institute, and there they describe, okay, which design provisions you should take for which products, more or less. And then once it is mentioned there, it is mandatory in Germany. So I'm not sure how that is, for example, in the UK, in France, in Spain, in Italy. However, from a point of view of a civil engineer, you always want to go to bed and sleep nicely in the evening. And for sleeping nicely, it is always good if you use the state of the art. And if you look, for example, in this example of adhesive anchors, there the state of the art changed pretty much, right? So if you have some anchors with a large percentage of sustained load, then the state of the art says, watch out, your resistance may decrease depending on the product you use. So if you want to sleep nicely in the evening, you should give it a thought, independent of the fact if it is already legally binding or mandatory in your member state.
Okay, thank you. And one last question I think is important. Can you please ask again why the mass concrete is the main parameter for carrying the load, and also why what influence does the rebars have on it? So when we make load tests, the underground, the base parameter, the concrete.
Yeah. Very good question. I think we could talk about that one something like 2 hours. In general, it goes back to the question that fastening technology is one of the only disciplines in design in reinforced concrete where you rely completely on the tension capacity of your concrete. Which means finally, if you have post-installed anchors or the other way around, in structural engineering, you say the concrete is for compression and the rebar is for tension, which is not possible for post-installed anchors, for example, because you don't know exactly where the rebar is, and the concrete cone starts relatively deep in the concrete. At the end of the embedment, usually, if you look, for example, at a head start or a friction-based system like a through bolt or a bolt anchor. And there usually you don't have enough reinforcement, and not really the reinforcement where you need it to cross the cracks of your concrete cone. And for that, you rely really only on the tensile capacity, which is conservative assumption. And then in special cases, you can utilize also your reinforcement. That's very rough and very general. As I said, maybe it's some topic for the next webinar. We could talk about that one alone, 45 minutes, I would say.
Yeah, okay. We invite you again. We like to. Thank you.
Okay, then.
Coming to the last part now, before we jump into the software.
Yeah, exactly. So I promise you the last part is relatively short. And then, yeah, we still would like to show you some additional design examples, hoping that you don't head off directly for lunch. Perfect. One additional change which also gives you improvements in terms of utilization degrees and advantages if you apply EN 1992-4 are the interaction equations. So here in the first part of the slide shown is the old interaction equation of the design guidelines, which shows a linear interaction equation on top and then an exponential approach in the middle, and you have different exponents for steel failure and for mixed failure mode. Interaction you always show with a combined design proof where you take the ratio between action and resistance, which are called here beta N and beta V. And in the old guidelines, you always had to take the maximum utilization degrees independent of the failure mode. So what happened is you usually mixed in this interaction equation steel failure with the concrete related failure mode, which is conservative, but in some cases too conservative. So there EN 1992-4 improved it. And in EN 1992-4, you always have to do two different design proofs for interaction, which is always one for steel failure with the quadratic interaction equation, and then additional one for the other failure modes. Now, what does that mean? Try to show that in one graph where you show the design resistance and tension on the y-axis and the design resistance on shear on the x-axis. And you see already that in tension, concrete failure gives the lower value compared to steel failure, whereas in shear, steel failure is decisive. So the old interaction equation required that you do this line 1 if you did it with a linear interaction, which is relatively conservative. If you work now according to Eurocode 2 part 4, then you do first the interaction equation for the steel failure, which gives you this dotted dashed line, and then you have the additional interaction proof with the bolt line, with a black bolt line for the concrete related failure mode. Now the final design proof is then the combination of the two, which gives you this red line, which is called curve 2, which gives you finally the function of the utilization degree. And you see already that the area in between the lines 2 and 1 you gain if you work according to EN 1992-4 in terms of additional performance. Good.
So the literature, if you want to dig deeper into the topic, we can provide you that list. That was something we brought together, but probably has not is not fully complete. So, but we can provide that for you. Also, if you want to further deep dive, we prepared a white paper. You already opened that now. So this is on the importance of the new DIN EN, or the EN 1992 part 4 standard for design of fastenings in concrete. We will not go through that. That is 20 pages, but here you can further deep dive on all those topics, and we can provide that to you at the end. When we end the online seminar, then there's a short survey. Just type in you want to have that white paper, and then we provide that to you. Now, what we also promised you, that we jump in our software. This is the Fixperience suite with several modules. One is CFix for anchor design, as you can also see on the picture here. And when you open that, then you see that. You can change the country here. It's still in Germany, but you can also change to your country, and the language is now in English. What we are going to do now, we have 3 examples that Thilo will show you. First of all, there is the psi-sus factor, and there we have prepared a chemical anchor, the FIS-V, an all-round mortar for concrete, also for masonry. And yeah, probably you can describe a little bit.
Perfect. Yeah, that's an adhesive anchor, FIS-V, in a group of 4. Embedment is relatively deep, 300 millimeters. And if you want to see the changes now, design method is EN 1992-4, which you see on the top left. Then there's a load of 250 kilonewton applied, tension load. And then if you look at the utilization degrees, currently, if you design according to EN 1992-4, the situation is overloaded by roughly 20%. If you change now to design according to ETAC, then you'll see that the utilization degree reduces to below 100%, and that is due to the fact that the load is reduced by this reduction factor of psi-sus, which I explained to you before, which we as a manufacturer recommend that you consider the design with the psi-sus in the future. If you have applications with a big amount of creep-inducing load, then it is.
Right.
We recommend to use the new design method.
So that was one where you already see why you should use the latest state-of-the-art design method. Then the second example will be also following our slides, was the MN factor, which can have a positive influence on your anchor design. And yeah, probably you describe also a little bit this example.
So that is an example for a bolt anchor for CMN. You see already that you need relatively small spacings that you can activate it. Design is now according to EN 1992-4. If you look at the utilization degree, is below 100%. And if you look in the results, now it's getting pretty small. The factor CMN is 1.19 in this case, which is due to the fact that you have a compression force under the fixture and that your inner lever arm is relatively small. If you change now to ETAC design, then you'll see that the utilization degree increases to 112%. So it is overloaded, and by designing with ETAC, you would need to change either your anchor configuration or your anchor type to get the load transferred.
So the last example then will be the interaction between type on no. Okay, that's not a problem. Okay. Yeah.
Perfect. So last example for today, and then I think everybody's going to head for lunch. Almost is the interaction equation, and there we have again a group of 4 anchors with a through bolt. We have a tension load of 50 kilonewton and a shear load of 111 kilonewton. Design is currently ETAC design. If you look here to the utilization degree, the situation is overloaded by roughly 6%. If you change now back to EN 1992-4, then you'll see that the utilization degree decreases to below 100%, and you can realize this application in practice. And this is due to the fact that the interaction equation is performed now in the future always with the 2 design proofs, one for steel failure and one for the other failure mode, which you see also here in the details of the results.
Yeah, thank you, Thilo, for the explanations. You could say now we have Eurocode 2 part 4. Why have you still the old ETAC in your design software? That has 2 reasons. There might be some projects where you still have designed according to the old method, where you're still allowed to use the old method. That is one point. The second point, also to give some good gut feeling to engineers, they compare, this was the old, this is the new one. And to make that easier, we still continue for a while to have both design codes in our software. The clear recommendation is that you only design with the new one. If you don't know, if you don't have the software, what I don't hope, but if you want to have that software, that is not a problem at all. You can register quickly, and then you can download it and install it. And very soon there will also be an online version. We are working on that, already released in Germany. Now more countries will follow. Then you only register once at the platform fischer, and there you already find the icon that you can start the design software. Probably there are some more further questions.
Yes, there are, and I would say I would ask you 2 more questions because of the time. Another hint is that I just get an email that the white paper is now called EN, not the German DIN anymore. It's improved, and if you want to download, it's an original version. Perfect, done. Thilo, yes, one question which came several times. Can you say please one thing to the standoff installation with shear loads and also seismic together with standoff? Why is it not included in the Eurocode, or how is it included?
Very good question. Big headache. To make it short, in terms of seismic, there's not enough research work done to justify, to include standoff installation under seismic conditions. And then this question if standoff installation is allowed close to edges or not. I discussed that with several experts which were heavily involved in the development of EN 1992-4, and I said, look, why don't you allow it in EN 1992-4 now standoff installation close to edges, because it's explicitly forbidden there. And before it was not really forbidden, and they said, but it was also not allowed, and it was never meant that you can use it close to edges standoff installation, which is then a bit difficult. So in general, what we do in our design software is we offer the possibility to design standoff installation also close to edges and give you a warning finally. In general, standoff installation is a very conservative or a relatively conservative design proof with relatively rough reduction depending on your lever arm. So hopefully it's going to make its way soon in the future into EN 1992-4. We're currently trying to do some tests on it, on how it really behaves in practice if you have this application. But it's a good question, pretty difficult issue.
Yeah, thank you. Another question, is the post-installed installation also included in the Eurocode?
Yeah, sure. Post-installed anchors are included in the Eurocode.
And I think this is exactly the point. Post-installed anchors, you have to separate post-installed anchors and post-installed installation in what means rebar connections. And that's exactly the point. Please be aware that post-installed anchors are calculated as anchors, and you can use them also as rebar sticks in a certain length. But if you go in the direction of post-installed rebars, then you have to take another calculation method, let's say that. Yes, and the very last question I would like to answer myself, it was for a mortar, the fischer, the epoxy mortar, is it allowed to install it overhead? Is it possible? Is it not too liquid? So usually we say, no, it's not too liquid, it's possible. Of course, please consider the temperatures, the storage temperatures, which is always with all mortars between 5 and 25 degrees. It should not be more. It should not lay in the sun in your warm car, because then the hardness can be destroyed. And if you keep it with the storage temperatures, the cooler you storage, the less liquid it is. So it's no problem to take it overhead. Thilo, I want to say thank you very much for your presentation. There were some more questions. Please excuse that we are not able to answer them now, but we want to answer them. We go to you after the webinar, but you have also the possibility that if you want to have a follow-up training, if you want to have a CPD seminar, software workshops, or anything else, please be aware that you can also ask your local fischer company which like to support you in these things. This is where we are here. We are not here to sell only products. We are here to support you as good as we can. And so I really like to ask you, go to your fischer subsidiary, to the fischer company. You know those people. If not, then look for the addresses in the internet. We like to support you as good as we can. So thank you again, Thilo, Oliver, thank you for coming, for presentation. Thank you very much for your participation, for your questions. We wish you all the best and hope to see you again. Goodbye.
Thank you.
Goodbye.